The search for a superconductor that can work under less extreme conditions than hundreds of degrees below zero or at pressures like those near the center of the Earth is a quest for a revolutionary new power, one that's needed for magnetically levitating cars and ultra-efficient power grids of T. But developing this kind of room temperature superconductor is a feat science has yet to achieve. A University of Central Florida researcher, however, is working to move this goal closer to realization, with some of his latest research published recently in the journal Communications Physics, Nature. In the study, Yasuyuki Nakajima, an assistant professor in UCF's Department of Physics, and co-authors showed they could get a closer look at what is happening in strange metals. These strange metals are special materials that show unusual temperature behavior in electrical resistance. This work is important because insight into the quantum behavior of electrons in the strange metallic phase could allow researchers to understand a mechanism for superconductivity at higher temperatures. Unlike a conductor, they have zero resistance, which, like an electronic friction, causes electricity. To turn a conductor into a superconductor, the metal material must be cooled to an extremely low temperature to lose all electrical resistance, an abrupt process that physics has yet to develop a fully comprehensive theory to explain. These critical temperatures at which the switch is made are often in the range of -220 to -480 degrees Fahrenheit and typically involve an expensive and cumbersome cooling system using liquid nitrogen or helium. Some researchers have achieved superconductors that work at about 59 degrees Fahrenheit, but it was also at a pressure of more than 2 million times of that at the Earth's surface. In the study, Nakajima and the researchers were able to measure and characterize electron behavior in a strange metallic state of non-superconducting material, an iron PNIC tied alloy, near a quantum critical point at which electrons switch from having predictable, individual behavior to moving C. The researchers were able to measure and describe the electron behavior by using a unique metal mix in which nickel and cobalt were substituted for iron in a process called doping, thus creating an iron PNIC tied alloy that didn't superconduct down to -459.63 degrees Fahrenheit, far below the point. Please support my channel to grow by pressing subscribe button and the bell icon. We will notify you technological news. Thank you.